Thursday. And we're starting to think that that's probably because we're in different domains, me as faculty member and you guys as students, this is the only, I've attended several universities. This is the only one I've ever been to that has students and faculty on different domains. So what that means is I can't share stuff with you and you can't share stuff with me through that. So I'm in the process of figuring it out, or talking to people to figure it out so that hopefully you can see this, but mostly Whitney, this is for you because that's going to be pertinent. So what I think is going to happen, and I'm doing this anyway, I'm downloading them myself anyway after they're recorded, so I'll just post the actual video instead of a link to the video that's online. But I'm probably still going to forget to do that. That's a great idea. So that's really my plan for right now, to sort of go around everything that's happening, is just to post the recordings as a video from my computer rather than linking them to something in the internet somewhere. So, sound good? If you are going to miss class and you can attend live, say you're on a bus and you feel like you can listen or watch class while you're on the bus, you can log in live in that class meeting in the Teams link in Blackboard. That will work. No matter what email, you have the link so you can get in. But apparently you can't see the recording. I don't understand that, if I'm being really honest. But anyway, the recordings will be available to you. As it stands right now, there's a little bit of a hiccup, but we'll figure it out. And you're here today, so I'm not worried about it at this moment. I do think that I'm going to have you guys turn in your first written paper homework assignment Thursday. Yes. And if that is panicky for you and you guys need till Tuesday, that's okay. But I want us to get in the habit of doing homework, so I wanted to make it Thursday. It's 10 questions. That's doable.
2.1, 2.2 in 2 days?
So
I crammed it all today for nothing?
You're done with it?
Yeah, I thought it was due today.
The online homework is due today. The web assignments are due today. The paper homework we did not have a due date for till maybe right now.
Okay.
Yes, and we'll say that it's midnight Thursday, so I guess midnight Friday. 11:59 Thursday. So if you do have questions, you can ask me in class on Thursday, right? And then turn it in sometime after that, or before that if you don't have questions. Are we tracking? Yes? Yes, Charlie. Sorry, Charlotte. I combined those words there. But I'm really glad you did it. Aw. The written homework 2.1, 2.2, that's written homework number 1 on this thing. We're going to have that due on the 18th in the nighttime. Yeah? And if we're being real honest, I'm probably not going to grade it till the weekend. So if you turn it in on the 19th, that's okay. Just sometime by the end of this week. Okay? Sound good? And your web assignments for 2.1 and 2.2 are due tonight at midnight, or 11:59, sorry.
So on the paper homework, from the book and everything, and if it has A, B, C, D, some of them will have a show answer, and some won't.
Yep.
I'm assuming you want us to do.
I should do all of them. If the answers are there, great. Use it to help you, but actually do the problems still.
Okay. So I skipped the ones that showed the answer. I'm because then I could just copy it down.
You could, sure. But at this point, that's not really what the homework's about. So I'm assuming that you're still going to do it and use it to check yourself, right? Right? Yes?
Oh, surely we can do that. All right, then.
I purposefully assign some problems where the things are given to you because I want you to, if you're struggling, I want you to look at it. I want you to use your resources to help you learn. I don't want that to take place of you learning, but I want it to help you learn, right? So if the resources are there, if it shows you the answer and maybe shows you steps like it would in the back, that's helpful. Use it. Still do it. Yeah. Okay.
I was just thinking I used that one to see what kind of answer was expected.
Right. Yeah.
But I was since that's already given, I thought that'd be redundant to have to do it. So I guess I should go back and add that.
Yeah, I would. I mean, redundant isn't necessarily the word. Perhaps it is, I don't know. There's a help for you, right? Yeah. Okay, so you think you guys can do that by Thursday? Nobody's panicking. You are panicking, Logan?
No, I'm like,
You can do it. I asked an or question. I didn't know which one you were answering. Marina, you're good? Okay. Kaylee, what do you think? Okay, cool. Sounds good. We're going to do it. Y'all are going to have homework 1 due on Thursday. I'll answer questions in class about it if you have them. Sounds good. Let's get going on this. We are on page 8. That's where I have us anyway. I hope you're there also. So we did truth tables and some logical equivalence stuff. I would like for us, maybe for our start here, why don't we do just the columns for number 1, and then we'll actually do the truth table for number 2. So we won't do the whole truth table on number 1. We'll just set up the columns. So what columns should we have on number 1? What 2 columns should we start with? P and Q. Good. Okay. And then what else do I need? What would I need to actually compute?
Not Q.
Not Q.
P or not Q.
Yeah, P or not Q.
You probably need not P as well.
You need not P as well.
And the whole thing is the last one.
Yeah, I'm going to make this 1 and this 2 and do 1 implies 2. Is that cool? Okay, so those are the columns that you would need for number 1. And that's the, no more, no less, right? You need all of those. Number 2 says to show that P or Q implies R, that those 3 equal that thing that's congruent to those 3 equal bars. So that those are the same. P implies R and Q implies R. So how do we show that 2 things are logically equivalent?
Fill out the truth table and see the 2 columns.
Yeah, we're looking at the 2 final columns and making sure that they match. Right? So we're going to do PQ and R. Oh my gosh. PQ and R. How many rows am I going to need in this truth table?
8.
I apologize for those of you who are going to have trouble keeping this lined up. I'm cheating a little bit with the iPad here. Okay. So, what other things do I need, and what other columns do I need in my truth table? Hang on, Ruth. Make somebody else talk, please. It's okay. Charlotte, you too. Y'all are both on a break. P or Q, Whitney says. Whitney, you would just want to keep going, or you want to leave it with somebody else?
You could do you finish the first one?
I probably would.
Just do P or Q.
Okay. And now you guys saw this. It was kind of a little fancy thing in your notes. There's like that double bar. That's to like indicate like, oh, I'm starting a different truth table here, but the first 3 columns are going to stay the same. Okay, so like the one we just did, that's our final column for the left-hand side of that equality or congruence. What? This is the first final column. Okay. I'm not going to write the columns P, Q, and R again because that's silly because they're going to stay the same.
Right.
Yeah. Okay. So that's just to mark like, hey, this is the last column in this truth table. I'm starting a new one. Okay, Whitney, you're still in charge.
P is R. And then
Awesome. Okay. So the first three columns, I'm gonna do the first two the same way I always do. True, true, false, false for P. True, false for Q. I'm gonna make R be true with all four of those. Oh my gosh, I'm struggling. Make R be true with all of those. And then I'm gonna list the P's and Q's again. So true, true, false, false. Q is true, false, true, false. And then R false with all four of them. Okay, now for this next column, I am doing an or between these two, right? It's P or Q. Now, what has to be true for an or statement to be true? Yeah, at least one thing needs to be true. Good. So we're looking at true, 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 false, true, 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 false. Any questions so far? No? We're okay? All right, that next one, I am looking at this column implies this column, which is going to be kind of weird. I've got to like go backwards. I got to do this. Now, what's true about an implication? This like arrow thing. When is that true? When is it false? Nope. Still on a break. Whitney, you're also on a break. You can look back in your notes. I'd be fine with that to answer my question. If you show up for work, you're going to get a promotion. If you show up for work on Monday, you're going to get a promotion. When is that false? You show up and don't get the promotion. Now look at where that is. The first part is true. The second part is false. That happens here, here, here. That's all, right? So those are false. The rest of them are true. Yep. When you show up for work and you don't get the job, that's when the implication is false. True implies false. So these guys, these three rows are the only rows where we get a false in this column. The rest of them are trues. True implies true is good. False implies anything is good. True implies false is bad. Okay. So we have our final column for the left-hand side of that like congruence thing. And now we want to figure out the other side. So we're looking at P implies R. So I'm looking at these two columns. There's like a lot going on here. True implies true is good. True implies true is good. False implies true is good. False implies true is good. True implies false is bad. And that happens twice there. And then the other two are true. These two, those two rows are a problem where I have true implies false. Oh no. So those are the only two rows where then I get falses in this column. Are we okay with that? Yes? No? You're shaking your head no, but very subtly, so I don't know. Okay, so then we're moving on to the next one. We're looking at Q implies R. So we're looking at these two guys. We have true implies true, which is good. False implies true, which is good. True implies true is good. False implies true is good. True implies false is bad. False implies false is true. True implies false again is bad. False implies false is true. And then for our final column, we have an and between these two guys. What has to be true to get an and statement to be true? Ooh, got a little wonky there. Whitney, you're on a break. What has to be true for an and statement to be true? Whitney already helped you. Yeah, they both need to be true. So we have that here and here and here and here, but not here and not there and not there, but we do have it there. Okay, so the question is, are these two statements equivalent? Marina says yes. Why? Because those two columns match. Yes? Okay, questions or comments about that? No? This here is a little factoid that I would, I don't know, highlight or write down or something. P implies Q is the same thing. If you want to make this not an implication, you can, making that not P or Q. Those are the same. Now, I have trouble remembering that. I'm going to be real honest with you. But the thing that I can remember is that the negation of this is that I show up for work and I don't get the job. Right? You see this? And this? How are those related? Yeah, it's De Morgan's law, right? The negation of this, the negation of this guy becomes P and not Q. Yeah. Right? So these are two things that I would write down to remember this thing and this thing. Remembering one of them gives you the other, so you maybe don't have to write them both down, but write at least one of those down and start it. And I think on your homework, when you're doing your homework, write it at the top of your page. When you make your note card for the test, make sure it's on there. This is a thing that gets forgotten, but it is helpful sometimes especially if you're trying to show that two things are equivalent. One's not an implication and one is, or whatever. You can make it not be so that it helps you simplify things down. So like number 4 is what we were just talking about. But okay. I would like for you guys to help me do this with that same thing in mind. The negation of P implies Q. This thing. Let me highlight this in yellow for importance. This thing. The negation of that implication. So we're going to write down the negation of the statement. If my car is in the repair shop, then I cannot get to class. So what is the first thing I know about this thing now?
Would be something like P implies not Q.
Would it be implies anymore, Logan, or not? Yeah, so the negation of an implication is no longer an implication. It's not if I show up for work, then I don't get the job. It's that I do show up for work and don't get the promotion, right? It's no longer an if-then statement. It is a P and not Q, right? So the negation of if my car is in the repair shop, then I cannot get to class is the P part happens and the Q part does not happen. So my car is in the repair shop and I cannot not get to class. Or I can get to class. Right? What's the only thing that makes this statement not true? Is that your car's in the shop and you still can get to class. Right? Right? So the negation of this statement is my car is in the repair shop. And I can get to class. The negation of the implication is no longer an implication. The negation of P implies Q is an and statement. Okay, how are we doing?
I'm confused maybe because like think about how you define Q. Because at first it's like, oh, Q is just not going to class.
Right.
That's the whole thing. So not Q would be going to class. I'm like, wait, no, it should be the other way around. It starts off not Q.
Yeah. So and like it doesn't have to. So I'm with you in that the double negatives get weird. And so often when you teach symbolic logic, you can't let any of your initial statements have a not in them. So that's its separate connective. So like this original statement is P implies not Q. And then you're negating that, which is P and not Q. So
And I guess it also doesn't help that the final statement doesn't really make sense. That you could get to class even though you don't have a car.
Somebody gave you a ride. That does make sense. My car's in the shop, and I found somebody who gave me a ride to class. Right? Like it doesn't.
Assuming this person has friends, like that's a bold.
I mean, I don't know. Maybe they walk to class.
Now we're assuming that they're that fit.
Maybe the car shop has a loaner, like a little van they drop you off in.
The Uber?
No, they have
Get
like
money?
the car shops have that. Yes, no one's gonna back me up here. Like Stokes Honda, if they're working on your car, they'll drive you somewhere in a minivan and drop you off, and then come and pick you up later.
It's wrong to have these assumptions.
That's not an assumption. The assumption is that you can get to class. However you do that, I have no idea.
I flew to class.
Flew, yeah. Maybe you have a jetpack. Okay, so what we're going to do right now is talk about some different ways to like mess with a conditional. So remember the conditional, I keep saying this word and I don't know if y'all know what this means, but the conditional here is P implies Q, or if P then Q. So there are basically 4 ways this can go. The converse of P implies Q is Q implies P. It's just backwards. The contrapositive, actually, let's skip to the inverse. The inverse is the negation of the P, so not P implies not Q. The contrapositive is both, backwards and negated. So not Q implies not P. Okay, so the converse is backwards. The inverse has the negation of the pieces. Think about the alliteration there. Inverse, negation, in negation. No, it doesn't feel like alliteration, but whatever. And then the contrapositive is the longest word. It's got the most stuff going on. What we're going to do right now is fill in our truth tables for each of those things. So let's do that. P implies Q, again, is only false here when true implies false. When P is true and Q is false. Q implies P goes the other way, so we got to do it this way. So that looks a little bit different. We have true, true, false, true. So what you notice right now off the bat, hopefully, is that, and maybe you already knew this, is that P implies Q is not the same thing as Q implies P, right? If it's raining, then I wear my jacket. If I wear my jacket, then it's raining. Those are not equivalent. So that's good that we recognize that. Okay, then we're going to do this. So the negation of P, I'm going to just do that. So false, false, true, true. The negation of Q is going to be false, true, false, true. And then we're going this way for not Q implies not P. So true, false, true, going backwards, true, false, true, 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 true. Sorry. We have false implies false is true, true implies false is not, false implies true is true, true implies true is true. So this is the conditional here. This is the converse. This is the contrapositive. This is the inverse. Anything you notice right now? They sure are. The contrapositive and the conditional are equivalent. All right, let's keep going. The inverse, false. For not P, I have false, false, true, true. And then false, true, false, true. Now I'm going this way. Not P implies not Q. So I have true, true, false, true. Anything about that stand out to you? The converse is equivalent to the inverse. All right, so our takeaways here is that the conditional is equivalent to the contrapositive. And the converse is equivalent to the inverse. The one that's actually helpful is this one. Later on in the semester, we're going to do proof by contrapositive. So perhaps the conditional is hard for us to prove, but we can prove the contrapositive. And that's, so the fact that they're equivalent is helpful. Okay, so I keep saying that P implies Q. I don't know if you've picked up on that or not, but this is obviously my go-to for reading off P arrow Q. All of these things are different ways to say if P then Q. Yeah. Some of these are kind of fun and just like slightly different. Notice this Q if P, P only if Q. Gross. The necessary and insufficient things are strange. Q unless not P. I don't know what world we're in there, but this one is kind of bizarre. We'll be doing this at some point too. Q whenever P. So like you can think about Q whenever P. So if P happens, then Q does. So it's weird. There are a lot of things happening here, but these are all equivalent ways to say P implies Q, or if P, then Q. Now, different people, and this is sort of this whole class, we're going to be learning how to write proofs. And what I'm going to expect at first is that you sort of adopt my proof writing style. But there's a style that we're all individuals, right? God made us all differently. We're all going to approach these things differently. We're going to pick different transitional words. We're going to pick different ways, like when we do things within a proof. You're going to have professors who lean on some of these more than others. I am going to lean on that yellow one mostly because my goal here is to be as transparent as possible. And I feel like that's the one that's most obvious, what is what. But you're going to have different people, and maybe not most of you because you're not going to have that many more math classes, but where people say different ones of these things to mean P implies Q. So anyway, this is there for you to refer back to if you need to. So here we go. We're going to write this statement as an if-then statement, and then we're going to write all of the other things. So the converse, the contrapositive, and the inverse.
I don't really understand P only if Q.
Yeah, so that the idea there is that not Q implies not P. That's the contrapositive. P only if Q. So if Q does not happen, then P does not happen. So not Q implies not P, which is the contrapositive, which is equivalent to the conditional.
So what would an example of that be?
We'll do it right now. Yeah, we'll do it right now. Let's write these down, get the P and the Q written down, and then we'll do that. Okay, so we have the home team wins whenever it's raining. I would like for somebody to help me write that as an if-then statement. So we need to identify the P and the Q. Yeah, it does. Because of this, right? Q whenever P. This is following this format, right? So Q whenever P.
Oh.
Yeah, so P is that it is raining. And Q is that the home team wins. Okay, so Whitney did this. Sorry, Whitney, I was not ready for you. Whitney said, if it is raining, then the home team wins. Okay, so the contrapositive is the one that's equivalent to the conditional. That's the not Q implies not P. Oh, now that was, sorry, Charlotte. Now that we have a P and a Q, we can do this. So P only if Q. That's the one you asked about, right? Yeah, so it is raining only if the home team wins. It's just a stupid way to say that, right?
It's like it could rain at any other time. It's not
Right.
Only if maybe it's the only.
It's the only, and that's why the other one is, this one is Q if P. The only is the issue. Yeah, so, and it's because of the, if not Q, then not P. P only happens if Q does. If Q does not happen, then P does not happen. That's the contrapositive, which is the equivalent to the conditional. The home team wins if it is raining. You can tell, like, that's pretty obvious. Like, oh, if it's raining, then the home team wins. But the only if Q part is yeah, the only if part is weird. So it is raining only if the home team wins. If the home team doesn't win, then it's not raining. Which is the contrapositive right now. So if it's raining, then the home team wins. The contrapositive is if the home team does not win, then it is not raining. Okay, and the converse is backwards. So that's a Q implies P, also not equivalent here. So if the home team wins, then it is raining. And the inverse is the negations of the pieces. So not P implies not Q. So if it is not raining, then the home team does not win. Now, I'm going to be real honest with you up front with you. It's hard to look at this and decide when you're just looking at the words, which of these things are equivalent and which don't make any sense at all, right? So it is easier for me oftentimes to to take what I'm looking at, write it symbolically, and then look at it that way, because I can get lost in the words and in putting my own logic on it. Well, that doesn't make any sense. Well, it doesn't matter what I think makes sense, right? It is what's written there, and so it's easier for me to look at the symbols, and that also helps me not attach my own feelings toward whatever the statement is. So if it's raining, then the home team wins. It's hard to see, like, okay, well, why is it not equivalent to if it's not raining, then the home team does not win? Well, you've seen from the truth table that it's not equivalent. So it's not. And you can come up with scenarios where that makes sense. So, but it is hard just looking at it. And that's the thing with the online homework. You're going to have, and Ruth showed me this last week, it's going to ask you, like, what's equivalent here? And none of it's in symbols. You're just looking at 6 options of weird variations of the same statement, right? And I think if put it in symbols and then look for those symbols, right? Instead of just reading all the options and trying to decide. Yeah, sometimes having those choices is confusing. So just answer the question and then find the choice that matches your answer. Does that make sense? Okay. Is anyone having trouble with web sign? Y'all know you're like in and fine. And know you have homework due tonight. Logan, have you done any of your homework?
There was one homework question where I think it had the right answer in 2 spots. You picked like the second one that wasn't there.
Oh,
Wait, it's the same thing twice.
oh,
Yeah.
there are really small differences sometimes.
Those are
It's
hard
hard
to
to,
read.
yeah,
It's like,
yeah,
It's not mine, but.
right. So the last logical connected that we had, like on the very first page or second page of what we were doing, was the if and only if. That's a biconditional. Oh, I'm not ready to tell you that yet. That's a blank, several blanks down. P if and only if Q. The symbols there, that's the arrow pointing both ways. You could think about that as like 2 separate arrows. It's this and it's this. Defined as true when what? Yeah, so they're both false. Yeah. Remember, false implies anything is true. Right? Yeah?
Yeah.
So, like, look at this. This is true, right? That arrow that way is true. But going this way, it isn't. Right?
Yeah,
However, this one's true going this way and is true going that way.
that's true.
Right. This one is false this way, but true this way. You need them both to be true, so that doesn't work. So it's true when both are true, or both are false. And it is false when either one of them is true. When only either one is false, we'll go with either one is false. Not both. Okay, so P if and only if Q is called a biconditional. It's conditional, but in both directions. And the corresponding truth table is this. So I'm going to do this, and I hope this is helpful. And if it's too much to look at, just don't. So I'm going to do P implies Q here, and Q implies P here. I'm going to call this 1. I'm going to call this 2. So P implies Q. I'm going this way. You can tell that in the second row is the only place where that's an issue, right? Right. True implies true is good. True implies false is bad. False implies true or false implies false is fine. Going the other way. So we're looking now at Q implies P. We got true, true, false, true. And then I would like to do an and between them. So that's true the first and fourth rows, but false in the second two, in the third, second and third. And that's the biconditional. So this is true, false, false, true. You need the arrow to the left and the arrow to the right to both work. That only happens in rows 1 and 4.
So how does, if and only if, I've always never understood.
That was really poorly worded. As we're in this class, there was a lot of things going on there. Okay, say that again. I have never understood. That would be a better way. Yeah, this is exactly what it is. It's that it means it works both ways. So we're gonna have this down here. The point is that going this way, it makes sense. Going this way, it doesn't if it's not biconditional. But oftentimes, we as humans will say statements that we mean as if and only if statements, but we don't say them that way. So, like, here's an example of one. I tell my kids, if you eat your dinner, then you can have dessert. If my kids don't eat their dinner and I give them dessert, did I technically lie to them? No.
What?
I didn't.
How?
I didn't say only if, right? Right? So what do I actually mean? You can only have dessert if you eat your dinner, right? You can have dessert only if you eat your dinner. Yeah? So that's a situation where we often treat it as a biconditional, but it is not one. Like you would tell me I was lying, but I wasn't because the conditional is fine. Because the first part didn't happen, it doesn't matter what the second part is, right? P implies Q. If the P part's false, the whole thing is true. It doesn't matter, right? So, but like this statement, if a function has a local extrema at x equals c, then c is a critical value of f of x. This is an if-then statement. It is not an if and only if statement. Because why? Because you can have critical values that are not local extrema. Right? If it's a local extrema, then it's a critical value. That doesn't work the other way. If it's a critical value, does not mean that it's a local extrema, right? So your arrow only goes one way. That's not biconditional. Yeah. So that's how this works. It's a if and only if. That means that one thing happens, the other one happens, or neither of them do. Let's do this example. John passes calculus. John does his homework. A, if and only if B. John will pass calculus if and only if he does his homework. Right? This one is an if and only if statement. So it's not just only if, it's if and only if. It's like synonymous with the other, right? If I tell you, it's sort of like a definition. If I tell you John passed calculus, you're going to know, well, John did his homework. Or John did his homework, well, that means John passed calculus. It's like that they mean the same thing. You can think about that as an equal sign, the double arrow. Yeah? If he does his homework. Okay. So that is the end of that. And we're ready to move to 3.2, I think. 3.2.3. Shoot, we're only on 2.3. That's fine. We're doing fine. Don't panic. Anyone, don't panic. Okay, so arguments. Okay, these definitions aren't going to make a lot of sense, but we're going to write them down anyway. An argument is a sequence of statements, kind of what you think it is, a sequence of statements that end in a conclusion. A valid argument is an argument in which the truth of the conclusion follows the truth of the statements. Those statements are called premises for an argument. Wait, what on earth does that mean? Great question. Here is an argument. If you are taking this class, then you are a student. That is premise number one. If you are taking this class, then you are a student. That is premise number one. Statement / premise number two, you are taking this class. Therefore, that's your hint that the conclusion is coming. This is your conclusion. You are a student. Okay, so I told you guys I like to do things in symbols to help me understand what's going on because it's easier for me to parse that than it is to look at all of those words. So if you're taking this class and you are a student, I'm going to call that P implies Q. You are taking this class, P. Q is you are a student. P implies Q. You are taking this class. That's our P again. Therefore, you are a student. That is our Q again. Structurally, this looks like this. Argument structures sometimes look like this, where it's got the premises and then like an equal sign bar line, and then the therefore, those 3 dots, and the conclusion. So premise 1, premise 2 equals basically your conclusion. Okay, what this looks like this is called the logical statement of the argument. What that looks like is you take premise 1 and premise 2, those together imply your conclusion. This is how you build a truth table with it. So you take premise 1 and however many you have, those together imply your conclusion. So for us here, this looks like P implies Q, that's premise 1, and premise 2, which is just Q. No, P, sorry. That those together imply our conclusion Q. Do you think that this is a valid argument? If you're taking this class, then you're a student. You are taking this class. Therefore, you are a student. Yes, it is. This form of argument is a common one. P implies Q and P, therefore Q. This is called modus ponens as an argument form. And it is valid, yes. I'm going to come back to this in just a second, but let's move on. Here's argument number 2. If you are taking this class, then you are a student. That's premise number 1. We're going to call that P implies Q. You are a student. That is premise number 2. That's a Q. Therefore, ready for our conclusion, you are taking this class. That's a P. P implies Q. That's premise 1. Premise 2 is Q. Those things together imply our conclusion, P. Do you see anything with this argument that does or does not make sense? It is not valid. Whitney says, why, Whitney, is this not valid?
Because Q doesn't imply P.
Correct. Q does not imply P. That's the converse, right? That is called a converse error in logic. Because P implies Q does not mean that Q implies P. Symbolically, that's what's going on. You have assumed that the converse and the conditional are equivalent, and they're not. If you think about this in terms of like the actual argument, let's talk about, say, I don't know, your roommate. Who's a student that we might all know? Who is a student that we might all know? Who is not in this room? Do y'all all know Alessandro? Yeah, let's go with Alessandro. We know Alessandro. Jalen, you don't know Alessandro. Okay, well, Alessandro is a math major. He's a good guy. Okay, Alessandro is a student. Therefore, Alessandro is taking this class. Well, he isn't. He is not in here. He is not taking this class. So we have found a student who is not taking this class. So this argument does not make sense. Good?
So I guess to be the one that implies, like the first one. For example, P implies Q, and then we have Q,
Mm-hmm.
and then there's a P. So like if it was like again P.
Yeah. It would be fine. So not all, this is two examples. These are common mistakes. So like these are two examples where premise one was P implies Q. And that's just to point out these like a common logic form, but also a common mistake. But the premise one doesn't have to be an if-then statement. It could just be like, I like tacos. Tacos are $1 on Tuesdays. That would be premise two. Therefore, whatever. Like it doesn't have to be an if-then statement for the first, for premise one. It's just that those two happen to be. But it's so that you can see like P implies Q. Okay, P happens, therefore Q happens. Like that makes sense. The fact that we have this thing and this, that doesn't mean that we get that Q implies P, which is sort of what that's saying. So yeah, if this was I don't know, if this was like a not Q, then this was a not P, that would be fine. And that's because the conditional is equivalent to a contrapositive and then yeah. Okay. So when determining if an argument is valid, you're going to assume that all premises are true, even if they are not. And the argument is valid if the conclusion is always true. That means you have a tautology in your truth table. We talked about that word already, right? Okay. The argument is not valid if the conclusion is sometimes false. Okay, we're going to go back and do truth tables for these things, but I want you to look at this. So symbolically, an argument has this form, P1 and P2, premise 1 and premise 2, however many there are, implies your conclusion, Q. If when you do this whole truth table, your final column, the final column, which would be this implication, if that is all truths, then your argument is valid. Now you can imagine the bigger the truth table, the harder this is to do. So there are some shortcuts. I'm going to talk you through some of this. So for this one up here, this is our final column. This is the goal. Yeah. If that final column, that's all of that, is all truths, then we're good to go. And the argument is valid. And it should be here because we already said it is. But we would have P, Q, P implies Q, P implies Q, and P. We're going to call that 1. And then we're going to call our last column would be that 1 implies Q. Okay, so we have true, true, false, false, true, false, true, false. And then our implication here, or our conditional, true implies true is good, true implies false is bad, false implies anything is good. Okay, so you guys can see now I have labeled premise 1 and premise 2, right? So P is premise 2, oh, whatever. Those are our two premises, yes? Now go back up to the definition of the argument is that it is valid when the truth of the conclusion follows the truth of the statement. Or the premises, right? So where do I actually care about what's going on? This is a really open-ended question, and I'm really hopeful that somebody can bail me out of this. But I said where the truth of the premises, the truth of the conclusion follows the truth of the premise, right? So where are the premises true?
Maybe P2.
Where are the premises, which is P1 and P2, where are they true? Just the first row. That's the only one, right? The this is true here and here. Those two are true. The other three rows, they're not both true. I only care about the conclusion in that row. Why?
Because he has to be
And all of the other truths I'm going to get for free. Why? They sure are. These are all falses, right? Yeah. So the false implies anything is going to be true. So those three rows I'm going to get for free in a tautology. The only rows that matter, the only row that matters in this one is the first row. And I want to know, does the truth of the conclusion follow the truth of the premises? I'm done. Does it? What's the conclusion? What letter is the conclusion? Q. And is Q true where my premises are true? Yeah. The truth of the conclusion follows the truth of the premises. That is a tautology. That's called a critical row, where all of your premises are true. Another place to catch that is here when you do your when you're doing your whole truth table. That one column where you put all your premises together with an and symbol. If you get a false there, it's not a critical row. If you get a true there, it is a critical row because all of your premises are true. If you get a false there, your implication is going to be true for free. Right? Because false implies anything is true. So I get those three rows for free. And then that last one I actually need to look at. So I have true implies true. That is good to go. So this is a tautology. So it is a valid argument.
Wait, why do we get the last three free?
Because false implies, because this is one, false implies anything is true. So false implies false, false implies true, false implies false. Those are all true.
Okay.
Because I don't care what the Q part is if the P part is false. Okay. So again, that's called a critical row. You could have more than one critical row. This is just an example where we only had one. You could have none. Anyway. Okay, so if you are, let's do the truth table for this one too. So you have our premise, our logical like statement, the symbolic logic here is P implies Q and Q, that these together imply P. So we're going to have P, we're going to have Q, we're going to have P implies Q, we're going to have, that's premise 1, this is premise 2. We're going to have 1 and 2, and then we're going to have, let's call this 3. 3 implies our conclusion P. Okay, so I have P and Q. I have premise number 1 is P implies Q. Premise number 2 is just Q. And then those together, I need with an and statement, and then the fact that those imply P. That's my last thing. Okay. So we have true, true, false, false, true, false, true, false. P implies Q. We have true, false, true, true. So if we stop there, do you see the critical row or rows? Okay, so Marina says the first one again, where we have both of those things are true. And the third one, right, where they're both true here. Now, what's the conclusion in this argument? The conclusion of the argument is what? What is the conclusion in this argument? It's P. You are taking this class, right? I want to know, does the truth of P match the truth of 1 and 2?
Should.
It should if the argument is valid. It does in row 1. Fine. This is a problem, right? This row 3 is an issue. The truth of the conclusion did not follow the truth of the premises. So this is not a valid argument. But let's continue this until you can see what's going to happen. Uh-huh. Yeah. Then the whole argument is ruined. Yeah. So you need all of them to be true for it to be true. But even one of them being false destroys the whole thing. So 1 and 2 here is true, false, true, false. Then that last column is our implication. So it's the premises implying the conclusion. So we are looking at, in this case, this column implies that this column. So true implies true is good, false implies true is good, true implies false is bad, false implies false is fine. This right here makes this not a valid argument because it's not a tautology. But you see how in rows 2 and 4, we get the true in the final column for free, right? Because this thing is false. It doesn't matter what the conclusion is because false implies anything is true. Yeah, so these two things are critical rows. Now, when you're doing a truth table with 8 things in it and it's long, you're going to want to look at the critical rows. Do you have to? No. You can do the whole truth table not even thinking about a critical row. And then look at the end and see, do I have any falses? Nope, cool, valid. Do I have a false? Yep, cool, not valid. You don't have to think about the critical rows. It can be helpful, especially if you have a very big truth table where you only need to look at those specific rows where the premises are true. Okay. Are we good? Fine-ish? Okay. So the argument in example 1 that we just did, I told you guys, is called modus ponens. This is Latin for something. Symbolically, it is written like this. I showed you that before. Show that this form is valid. We did this on the last page. Okay, so a valid argument can lead to an incorrect conclusion. How can this happen? This is weird, right? So if if any one of your premises is false, right? You're looking at this argument is this P1 and P2 and P3, blah, 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 to Pn. This implies your conclusion. If this is false, then the argument is valid because you're going to get all truths. You with me? Yes? No? If any one of these is false, it makes the whole beginning part of this implication or this conditional false. Right? This is a gigantic and statement. Yeah? If P7 is false, this whole thing is false. Right? And if the whole thing is false, well, false implies anything is true. So my final column is going to look like the tautology. The argument would look valid. The argument form structure is valid, but you made an incorrect, premise. Does that make sense? Let's give you an example, because probably not, but let's look at this. So if x is greater than y, then x squared is greater than y squared. Since the square root of 2 is greater than 3/2, then 2 is greater than 9/4. So this is a P implies if x is greater than y, then, so this is your P, then x squared is greater than y squared. Since since the square root of 2 is greater than 3/2, that's our P again, right? Therefore, Q. This is a valid argument structure. This is modus ponens. This is called universal modus ponens. We'll talk about that later, where you say something for a general thing and then you talk about it specifically. But, so generally speaking, if x is greater than y, then x squared is greater than y squared. Since for this specific case, x is greater than y, then in this specific case, x squared is greater than y squared. This works as argument structure. It is valid. It is a modus ponens situation. P implies Q, and P therefore Q. Yeah? P implies Q, P implies Q, and P therefore Q. Yeah?
Yeah.
However, this is not true
No,
because 2 is not greater than 9/4, is it?
the opposite.
But why? I made an incorrect assumption that we're treating as true, right? We're going to assume all premises are true for the structure of the argument. Yeah? Square root of 2 is not greater than 3/2. I made an incorrect premise. My premise is false, but we're treating my premises as true. So therefore, the argument structure itself is valid. However, I've reached an untrue conclusion because my premise was false to begin with. Great question. This, as an argument, it's valid. However, this is not true.
Is this kind of like jumping to conclusions?
No, I think it's more knowing what the question is asking, right? And why I think too, we do this in arguments ourselves. I don't know if any of you have a significant other, but these things sort of happen where I assume a thing to be true and make a conclusion based on that thing, and that thing's not actually true, but my argument makes sense if it was, you know? But maybe he didn't mean it that way, right? We do this a lot. The structure of the argument is sound, and we sort of die on that hill, right? But square root of 2 is not greater than 3/2, so chill, right? So the structure of the argument is valid here. However, we have reached an untrue conclusion because our premise was false. So you have to answer the question that's being asked. I'm not going to ask you something that's so convoluted, but to tell me if it's valid or not or whatever. But the idea here is that it is possible to have a valid argument structure and end up with an incorrect conclusion. Here's another one, which is trippy, that an invalid argument can lead to a true conclusion. This is our second bullet point right there. So let's talk about an invalid argument structure, and then we'll put some words to it. So an invalid one we know so far is that this does not work, right? P implies Q and Q, therefore P. That does not work as an argument. Can we come up with a statement that would fit this structure that would result in a true statement, but the argument structure is bad? How about this? How about I just give it to you? If John does his homework, then he'll pass. He passed. Therefore, John did his homework. I should use an actual person because I can assure you that this has happened, that students will take a class and not, well, maybe John did do his homework, but the structure is still bad for this argument. The conclusion itself that John did his homework is maybe true, but the argument here doesn't mean that, doesn't imply that. Okay, so those things are weird, and it's maybe evident why we need to be careful about how we are speaking and what we are saying. And also when we're arguing with people to make sure we are right to begin with. In your textbooks, you have, this is table 2.3.1. So this is a table of rules of inference. This is what this is called. So if you have these two things as your premise, you get these conclusions. So this first one is modus ponens. Again, it's just backwards, but this is Q. This is modus ponens. And then we talked about this a few minutes ago. You have P implies Q. That is equivalent to not Q implies not P. That's this argument here. So P implies Q and not Q, therefore not P. That is valid argument structure. That is called modus tollens, which is also Latin for something. That's again because the conditional and the contrapositive are equivalent. Okay. That third one, P implies Q and Q implies R. What do you think the conclusion could be? If P, then Q. If Q, then R. Yeah, it's, you skip the middleman. It's that P implies R. You get to use a transitive property here. That P implies R. You get to just skip that middleman there. Skip the Q. If P gives you Q and Q gives you R, if you have P, then you get R. Okay, this next one, I don't know what this is called, but if you have P or Q and you know it's not P, then it is most certainly Q. This is trippy. You're not going to come up with this, so I'll just tell you. P, therefore, you would think, but you can make it an or statement that includes P and some other things. This is fine. If it's P, then it can be P or Q, right? If you know it's P, then you know it's P or anything else. Because you just need one thing to be true. Then it's the P part. You don't care about the Q.
Oh,
That's called generalization, which makes sense. What'd you say, Charlotte?
Wouldn't that be true for any of the other ones? I could add B to like the first one or something, or B.
Yes,
And just add to any of them.
correct.
And this one I could just keep adding or.
You sure could.
It's tricky.
It is. As long as you got P, if P sticks around, you can put anything else with it that you want.
Oh.
With an or statement, right? Don't do that with an and. How about this? It's P and Q. This is called generalization. Maybe this will help. This is called specialization. This, you can do P, but you could also do just Q. I'm just choosing one. Right? If you know it's P and Q, then you know for certain that it works for P. Okay? If it's P and Q, it's P and Q. Yeah. That's good. That's a good one. Okay, so this is P or Q and not P or R.
So Q and R?
It's Q or R. Oh gosh, I hope it's or R, but now you're making me think, Charlotte, maybe that's supposed to be and. No, it's oof.
Broker.
Charlotte.
What
you do? What you broker?
What'd you
It's supposed to happen like this.
Why did we think the R, the and goes away?
The two Thomases are car in case one breaks.
Yeah, back up.
Yeah.
We're gonna write it down for right now. We're gonna write it down for right now. But I'm gonna look it up when we leave here today. And we're gonna make sure that's not supposed to be an and. Okay. Yeah, give your homework, do that so you can ask me crap, so that you can ask me questions about it. I would be happy to answer those either via email or at the beginning of class on Thursday. We have, how far behind are we? It doesn't matter, it's gonna be fine.
Our first test is on Thursday. I tell you.
How many classes does that mean we have? I'll figure it out. I think we're gonna be okay.
Thank you, I haven't thought that far.
We haven't-
The two classes is 5. So
Including, so we only have 3 more.
1, 2, 3. Yep.
All right, y'all have a good day. I'll see you on Thursday. I'll let you know if anything's changed by then.
So Matt is changed by then?
No.
So much fun.
3 classes left.
All of the people.
Get through that.
Okay, we gonna do, you wanna have an album?
I got class with at 6 p.m. and 9 p.m.
Dang, wow.
That's
every day.
Oh, it's a class.
Yeah, night class.
I have a night class too. But it's principles.
What
Oh, go principals class?
times?
Advanced networking.
The date,
Network security.
Hi, the date on Thursday is the
6
18th.
p.m. to 11 p.m.
What? Ain't no way. I am not.
Thank you.
You're welcome. Oh, I think we're gonna be fine. I hope we're gonna be fine.
catch up somewhere.
We what?
We're gonna catch up somewhere.
I hope so.
I think